Hello everyone, we are Magnetum and this is our P3 presentation.
So the list of the materials we will need during creating our product include ND magnets for levitation and frictionless motion, DSL enameled electromagnets for acceleration and speed control, PLA plastic for base plating and the experiment body, optic sensors for motion control, and enamel wiring for wiring and programming. Some of the tools and equipment we'll be using during the production of our product include soldering tools, a multi-sim breadboard, wires, post-width modulators, and programmable software with NSQDEC compatibility. Some of the skills that we will need include coding, 3D modeling, electrical engineering, craftsmanship, physics, logistics and legalities, and website/video design.
So in order to make sure that our solution works, we have a list of sort of things that we have to know that we have to hit. So we have to make sure that we can control the motion of our train. That is test 2. Test 1, we have to make sure that we can actually make our train hover. That's sort of the basis of our entire project. Test 3 is we put them together and we have a very rough hovering and movement control. And then test 4 is the refined version of that. So we'll have our, maybe not our entire track, but we'll have a section of it where we can successfully hover the train and move it back and forth without it being unstable.
So for our subsystem controls, we do have 4 tests. Our first subsystem is to control the actual movement of our magnets and of our loads of our trains. Test 1 and test 2 are focused on that, on making sure the locomotive, we have proper control and we can program a system to accurately move it from one end to rail to the other, just as a basic for it. For the experimental side of it, Max. For the experiment, we will be using a series of coils from different powers to see how much control we have on the levitation height for test 1. For test 2, we'll be using different types of enamel wire with different variations of separations to see how fast we can get the load to move across a specific bar rail, and that'll be our 2 experiments to see how much control we have over the movement of our magnets. For test 3 and 4, we'll be testing the motion, how well do they move along each other. So we'll be experimenting on Halbach arrays and linear induction motors to see how fast we can get them and how controlled we can be in that motion. For those experiments, we'll be using different testing standards. Max, if you may. For experiment 3, we'll be using different ND magnets with different orientations to see how much how uniform a hovering test is and how well that relates to motion. And for test 4, we'll be combining test 3 and test 2 to make sure we have the best scenario for all of them, making sure our prototype is the ideal prototype.
So here you can see our first test. Unfortunately, this is the only one we could get done in time because we hadn't had funding up until now. So in this first test, you can see we have a very small magnet hovering above our electromagnet, which is just enameled copper wire wrapped around multiple times. And as we turn it on and off, the magnet gets lifted and then dropped back down, lifted, dropped back down. And this is connected up to a power supply that's directly connected into a wall socket, a basic wall socket. In the second one, however, we have it connected to a battery with a lot more voltage, and we have a bigger magnet that we're actually lifting up. Same electromagnet though, same enameled wire wound around. But as you can see, when power is brought to it, it is lifted much higher up, and it's a much stronger push against it. So here are the results for the entirety of our test 1. So for the first 2 tests, we use just regular non-enameled copper wire, which means that when you touch the wire to itself, it does conduct. Enameled wire, when you touch it to itself, there's a very fine film around it, so they don't conduct. And so that means that when the wires are wound around each other, then it's not as powerful. So meaning it wasn't, the first two electromagnets were not strong enough to float anything, which means the total force was too small to calculate. For 3, 4, and 5, we use a enameled copper wire for our electromagnet, meaning it was much more powerful. And with 4.5 volts, we were able to shoot 0.8 grams, 15 centimeters in an eighth of a second, which resulted in 0.076 newtons of force. In 4 and 5, we used two different voltage, but this time instead of just a pulse of current, we had a constant current, which lifted 4 grams, 2 centimeters on 3 volts, and 3 centimeters on 4.5.
So some additional testing data is that because our tests are so technical and need very specific materials, we did not go out and get the materials. We were waiting on CMS and to use our CMS so we can use our funding to actually get those materials and get a better and more accurate view on how our prototype would be using those sets of materials. So we're waiting for neodymium magnets and a set of 12 and 40 pound electromagnets for all of our tests.
During the development of P3, we added several specifications to our list of specifications, including our design, a design that is stylistic to the 1950s, a scaled down model that represents a full scale model that may be used for testing, designing stopping mechanics that are smooth and comfortable, ensuring potential passengers will not be exposed to danger, whether that is immediate or delayed in effects, and making sure our prototype is mobile and does not require certain electrical parts, no transformers or no breakers. Testing standards that we used that considered were included standard test method of high coercivity permanent magnet materials using hysteresis graphs, standard practice for electromagnet sorting of ferrous metals, standard specifications for 3D image data, exchange, measurement procedures of magnetic field levels generated by electronic and electrical apparatus in the railway environment with respect to human exposure, and guidelines on limiting exposure to electromagnetic fields.
So to be able to fit with all the data we had, we got a new mentor, Dr. Javier Huelacup. He is a physics doctor, and he helped us with the design of the theoretical building of our system. So with the physical forces and with the electrics of it, he helped us find out what would be the most effective way to use linear induction motors and how we could transition those into superconductors in the near future. He oversaw our technical designs to make sure that they were not only feasible, but efficient, and that we could build them in the time span of the project.
So as our project advanced and moved along, we had to make some corrections, modifications to our designs, both on the technical side and the aesthetic side. As far as the technical changes, we decided to change to magnetic rails, so 2 rails going along our entire track as opposed to one solid bigger one. And we also decided to change our carts to have a small hole in the bottom, or a sort of a cubby to house our electronics, and in best case scenario, a superconductor. And we also decided to use a linear induction motor to pull the cart along, which is basically just a bunch of electromagnets in a line. And we also finalized material and energy consumption, so we decided what it's going to be made out of and how we're going to power it.
On the aesthetic side, we decided on the 1950s aesthetic for the project. As you can see in the picture, those are our prototype designs. They're modeled after the 1960 Hummingbird and the 1954 Volkswagen van trip. And apart from that, we actually finalized our design theme, and we got far along with that. We also finalized how big our prototype was going to be and how we were going to control it with a centralized control hub. Thank you. These are our citations, and thank you so much.
Thank you.